Yeah, okay. So, hello everyone. This is the Qwen Image paper, or a technical report rather. So let's get started. So, uh,
Oh, wait, wait,
the
wait.
abstract,
We have a volunteer for next week, Venki.
Yeah, thank
Sweet.
you.
Awesome.
Let's go.
Are you on the Discord?
I think I'm on the Discord. If not, I'll add myself.
Yeah, I mean just announce that you are what paper you're going through next week and just drop the link to the paper so that people can pre-read this.
Okay, sounds good to
Super
me.
excited for you to share, Venki. Looking forward to it. Thank you.
Thank you, Eugene.
yeah, well, okay. So, yeah, so we have Qwen Image. So it's a diffusion image generation model. That's pretty nice. Like throughout the paper, they talk about how it's a diffusion model, obviously, but they kind of put special emphasis on how the model does well in Chinese or like logographic languages, like including Chinese and others. And also we kind of get to see like how they curate their data and also like how they label it and like the different techniques that they use. Yeah, I find that pretty interesting. So let's see. So it's an image. So it achieves significant advances in complex text rendering and precise image editing. That's pretty cool. They use a progressive training strategy. So yeah, so with this, they use essentially curriculum learning. Like first they train the model on like very low resolution slash quality images, like 256 pixel or like 256 by 256 images, and they kind of like progress. Like they make the images like sharper and sharper, which I find interesting. So it's a form of curriculum learning. Let's see, English, Chinese. And they also use VAE, like a variational autoencoder, and also a language model or like a visual language model to to kind of have like a system one, system two thing where like they use a VA encoder to encode low level like physical or like spatial details within the image. And they use their language model like Qwen 2.5 VL to encode the more like semantic part of the image. So I kind of found that interesting also. So let's see, there's nothing new here. These are a bunch of benchmarks. You guys can read it if you want, but I'll kind of skip them. Bunch of images, pretty cool.
Yeah,
Yeah, so
the images are worth looking at at some point later. You can refer to them or pull it up yourself separately, you know. But like it's editing and generation that in both are like to a level I've never seen before.
yeah.
I
And if people
mean,
are interested, I can just like go back after like halfway through.
I think editing and stuff, it's been done before just in separate models, right? Like you need like a context consistency model. But yes, very cool. I thought the first page of images was very cool. Like this one with the whiteboard. You see how like the whiteboard is at an angle and then it has reflections and the text is at an angle and not directly straight. I was like, oh shit, this is pretty cool.
Yeah.
Quen dropped a teaser about edit today. This is a editing model, by the way. Um, it's very heavy on handwriting. Okay, let's just continue to.
Yeah.
I think you should read the descriptions of all these as well for what they show, by the way, for people following along. Oh shit, I'll drop the paper as well on Zoom chat.
Yeah. So let's see. Intro. So here they just talk about the challenges. They talk about like aligning model outputs with complex prompts and also like just essentially making the text look nice. That's kind of like what they're talking about here. And like sometimes they talked about how people have difficulty modifying images. Like if someone has like a pose, or if they want someone to strike like a different pose, they want to edit the image. Like the person will kind of strike the pose, but the background will kind of like lose coherence. So they kind of like they talk about that as like some of the problems that they're trying to solve with the making of Qwen. So they also put like a ton of effort into like data engineering right here, which we'll kind of like see in the paper. So progressive learning, I already talked about that. Multitask training paradigms, we'll talk about that. And they also talk about like how they use GPUs. They have like a really interesting structure there. So let's see. Yeah, we'll get into all of this. Yeah, okay. So here's the architecture. So for this is a diffusion model. So like they'll inject noise into it, like when they're training. When they're training, they'll patch some of the images and they'll train the model to um like essentially reconstruct it. And what they do here is they use like, well, we'll talk about it here, but they'll use like the language model to maintain like global coherence. Like they'll say like, oh, this image is supposed to be about this this image, and their autoencoder kind of encodes the fine like the lower level details. So they have like it's composed of 60 of these like transformer blocks, or not transformer. Yeah, the diffusion transformer blocks. And let's see, so there's nothing special here, or you can look at this, but they use QK norm, and they also like they made their own positional encoding like mechanism, which is MS rope, which we'll also get into. Okay, so let's see. So yeah, so there are three components. So they have like a multimodal language model that serves as the condition encoder, and it extracts the feature from the textual inputs. This is like the Qwen 2.5 VL part that I was talking about. They also have like the VAE, so it compresses images, like it just extracts the physical features, quote unquote, of the image. And they'll also have like the multimodal diffusion transformer, which is the actual diffusion part of the diffusion model. Let's see. So they talk about how they use Qwen 2.5 VL. Let's see. So they say that it has like they have three key reasons. So the language and visual spaces of Qwen 2.5 VL have already been aligned. And 2.5 VL retains strong language modeling capabilities without significant degradation compared to other language models. So I tried to like look up and like I tried to see what they were talking about with this part. I wasn't really able to find what they were talking about. So if anyone knows, like I would definitely like to know that. But yeah, so the third reason is that Qwen 2.5 VL supports multimodal inputs, so just image and text. Let's see. Oh yeah, and they use a latent space of or latent of the last layer's hidden state from Qwen 2.5 VL as the backbone. So they use that to like represent the user's input. So that's pretty interesting. Let's see. So as for the VAE, let's see. So they train an image VAE with 2D convolutions, or that's usually how this works. They usually train a VAE with 2D convolutions on a massive image data set to obtain a high quality image representation. But what they do differently is they use a single encoder, dual decoder architecture. So they use a shared encoder, oh no, shared encoder compatible with images and videos alongside separate specialized decoders for each modality. So that's what they do differently. And let's see what they also they also collected a lot of text-rich images. So like they talk about here how it's like PDFs, PowerPoints, alongside like synthetic graphic or synthetic paragraphs and like covering different languages. And they use this to essentially to train the model like later with post-training on RL. They use that to like train the model on how to actually follow instructions. Like, oh, if I want to make a PowerPoint with like this property and this property, they'll like use some of those documents. Let's see, they do that. Uh, let's see. Yeah, and for the diffusion part, let's see, they use a multimodal diffusion transformer. So they talk about how they have their MS rope, which is a multimodal scalable rope. So like the reason, well, I'll just read it first, but let's see. So in the traditional like diffusion block, text tokens are directly concatenated after the flattened image positional embeddings. So they're talking about like this. So like if your image is split into 9 pieces, then they'll just like concatenate the text after. But what they do is I'm reading from the blue text now. So text inputs are treated as 2D tensors with identical position IDs applied across both dimensions, and they're concatenated along the diagonal of the image. What that actually means is that they have their image here, and they essentially just pretend that the text after is like concatenated along this dimension. So they pretend the image is like, in this case, they pretend the image is like a 6 by 6 image. So that's what they do. And they say like the reason that they use this is because like previous 2D ropes, like with other implementations of their positional embedding, certain rows of positional encodings for text and image, the 0th middle row in figure 8b becomes isomorphic. So essentially the model becomes confused. They're talking about this part right here. They say like with previous positional encodings, the model kind of becomes confused and it can like confuse these like this middle row. So it can become confused as to which parts of the image correspond to text and which are actual like pieces of the image. Let's see. So this is where they talk about the actual like the layers. They talk about like the VLM, the VAE, and the transformer. So there's that. So 20 billion parameters for the diffusion model in total. Yeah, so wait, does anyone have any questions so far? I realized I didn't pause for input.
Nope, we're looking at chat. It seems good. You're doing
Okay,
good,
cool.
Omar.
I actually have a question.
Yeah.
So well, in the architecture diagram up a little above, I don't see any mention of, maybe I just didn't read it properly. No, sorry, in the architectural diagram
Oh,
part.
yeah.
Yeah, like up in the previous page, I think. Yeah. So I don't see. So is the diffusion process, like, how does diffusion come in here? Is it just that they're adding noise in the autoencoder and then removing the noise progressively on the unpatch, like using the transformer blocks, or is there something more complicated there?
Yeah, so someone correct me if I'm wrong here, but like I don't see how they actually like I don't see which diffusion objective they use, but like to my knowledge, a common diffusion objective is like not to reconstruct the image, but usually they'll estimate how much noise was added. Like first they'll like with the forward pass, they'll like corrupt the data. Like they'll gradually corrupt the data using a specific amount of noise at each step. And like with the backward pass, instead of like actually trying to reconstruct the data or like, reconstruct the image or whatever modality it is, they'll try to estimate how much noise was taken away in that step. So I don't
Yeah.
know if they put it here, but I wasn't able to find it.
Yeah, okay, so so it seems like it's just in the training regime and adding the noise. Okay, understood. Thank you. That's helpful.
Yeah. Any other questions? Okay, cool. Yeah, so now we go on to the data collection. So in here, they actually put a lot of effort into data collection and curation. Well, I'm sure all companies slash labs put effort into this, but like we're able to actually see what they do to actually curate their data. So they collected and annotated billions of text image pairs. That's cool. And they prioritize data quality and balanced data distribution. So they try to create like a well-balanced and representative data set that closely mirrors real-world scenarios. So that's interesting. And they categorize it into like 4 categories. So nature, design, people, and synthetic data. And like it's important to note, they say it like somewhere here, but it's very important to note that when they say synthetic data, they mean like PowerPoints and stuff like that. They do not mean AI generated content. They take extra care to not include AI generated content like in their data mix. Yeah, so we'll just go through each of these. So they have their nature category. So it says like 55% of the data set. They have like their objects, landscape, cityscape, plants, animals, indoor, and food. So also it has like content that doesn't clearly belong to the people or design categories. So that's cool. So with the design category, oh, they also have like a graphic here, but I'll look at that. I'll look at that later. So they also have like their design category. So it's 27% of the data set. So it's usually like posters, UIs, presentation slides, and like paintings, sculptures, arts and crafts, and digital arts. So like this, they say that this helps the model to form like to emulate slash replicate different art styles. So that's interesting. So they also have the people data set. That's 13% of the data set. So they pay special attention to this because that's like portraits, sports and activities, and just like humans doing different things. So they say that it helps the model to generate realistic and diverse human images. And finally, the synthetic data set. So it's around 5% of the data set. So again, like I said before, it does not include images generated by other AI models, but it's like data synthesized through controlled text rendering techniques. So it includes like, let's see. Oh yeah, so they adopt a conservative stance towards such data as training on low fidelity or misleading images may weaken the model's generalization capabilities. So yeah, so let's go to the graphic. So this is like a visual representation of like of the proportion of like the nature, the different classes and the different like subclasses like object, cityscape, etc. Yeah, so that is that. So yeah, they have data filtering. They have like I think like 7 to 10 stages. How many stages? They have a lot of stages of like filtering and pre-training. So this is kind of like I get the gist from reading this section that they had like 7 to 10 stage filtering process, but they also started doing curriculum learning at the same time while they were filtering the data. I'm not sure if that's actually the case, but that's kind of what it seems like from here. So let's see. Oh yeah, they have 7 sequential stages. So yeah, synthetic data
They
is introduced from stage 4. Yeah.
they mention it in the abstract that it's kind of important, right? So they adopt a progressive training strategy, and then they kind of go through their stages, right? So there's non-text to text rendering evolves from simple complex textual inputs, gradually scales up to paragraph level descriptions. So they do have like this curriculum learning, and it's kind of it builds from simplicity to more advanced stuff to like the most niche little synthetic data.
Yeah.
They
Cool.
cover it later too, yeah.
Okay, thanks. I appreciate that. Yeah, so I was like, I'm not gonna go like super in depth for each stage. But like, so let's see, they have the initial pre-training data. So like this is what I talked about or referenced earlier, where they trained on like very small images, like 256 by 256 pixels, like various aspect ratios, so they kind of list them there. So they also like remove low quality and irrelevant images. So they make sure they remove duplicates and they remove like really, really low quality images right here, and also NSFW stuff. Yeah, let's see. They also, let's see. So onto stage 2, they focus on improving the image quality. So they remove images like with significant rotation or flipping. This part. Uh, let's see. They describe like blurry or out of focus images, excessively bright or dark, or images like with unnaturally high color saturation. They also remove images with like low entropy, so that's just like only black or only white images or whatever. And they discard images with overly complex textures, or yeah, which is associated with noise or non-semantic patterns. So this is also a graphic of like of their filtering process. Yeah, so stage 3, let's see. So this is actually where they do or where they talk about some of their annotation. So here's where they start to focus on text. So they start to focus on improving the alignment between textual description and visual content. So I'm reading the blue part here, but they have like 2 splits. So they have like captions provided by websites as well as metadata such as titles or tags originally associated with the images. So they also have, let's see, captions generated by Qwen. So like they also use Qwen to help in their like data annotation process. Let's see. So this is just talking about how they also combine raw captions and synthesized captions. They also discard just like trash captions, like really long captions or like generic ones that's like, sorry, I cannot provide a caption, indicating that the caption is broken or something else is wrong. So they also talk about, let's see, text rendering. So this is stage 4, text rendering. Interestingly, they split their languages into English, Chinese, or other, which I did not expect, but apparently it worked for them. Let's see. Yeah, they address challenges such as low frequency characters, mixed language scenarios, and font diversity. So they incorporate synthetic text rendering data. And let's see, they also remove images with overly dense or excessively small text. So they do that to increase their text quality. Oh, and this is also an interesting graphic where they show kind of the distributions on some of their filters, and you can kind of see the examples of some of these images. I kind of found it helpful. Yeah, so stage 5. So they talk about how the model transitions to training with images at 640p resolution. So they're increasing they're making their images sharper and just increasing the resolution, presumably to make the training more stable. So they also apply more filters. So let's see, they try to remove images that have like overexposure, underexposure, blur, or compression artifacts, or all poor composition or visual appeal. They also remove images containing watermarks, QR codes, and stuff like that. So stage 6, they kind of focus more on portraits. Let's see. Yeah, so they categorize their dataset into 3 categories, so general, portrait, and text rendering. So that's what it sounds like. Stage 7, this is balanced multi-scale training. So again, they're increasing their resolution. And interestingly, they design a hierarchical taxonomy system for image categorization. So within each category, they retain only images with the highest quality. So here, this is essentially like data QA. So just making sure that their model doesn't generate really bad images like of a certain type. So like they build a tree of all, of all like objects that they have, and they just essentially check like, oh, are like when the model generates buildings, do the buildings look good, etc. Like do the landscapes look good, do the parks look good, etc. They do that. They also, while they're like within each category, they retain images with the highest quality, and they also allow, like they make sure to balance their data so that they allow the model to retain previously learned general knowledge and ensure stable convergence while adapting to high resolution images. So presumably this is to combat like catastrophic forgetting, where your model like, trains on a specific subset of data, but like kind of loses its generality. So that's what they do in stage. Yeah, stage 7.
Yeah, I think stage 1 to 7 really shows how much care they put to cleaning the data, whereby they had so many simple filters just to check for resolution, check for cropping, check for flipping and everything. And that's what led to this strong model. Actually, then the question becomes, hey, if we had left that data in, would the model be just as good? It's unknown. I don't know if we would actually deliberately train a model on bad data. But I mean, their pipeline is actually quite fascinating.
I think in
Yeah, I
one
agree.
they share some stuff with like why they don't do synthetic data from images generated by other models and noisy stuff, and they say that that would harm the quality, right?
Yeah, because there's a lot of
So
artifacts, right? Yeah.
exactly. So if you train on poor quality data, you will not get good model. But that's it seems necessary to need to do all this then.
Yeah, that seems so. And if we look at figure 10, right, I think like they shrank their data set maybe by by 2/3. So a lot of it is really just it's
Yeah.
filtering, and I really enjoyed figure 10. So it really just shows you how much care needs to be taken for doing this.
Yeah. Yeah. So does anyone else have any other like questions or comments?
Did they mention if this is a semi-automatic filtering? Because it's billions of images, and it's a huge effort to annotate and filter based on quality and all of this.
Yeah, so they like in the technical report itself, they just talk about, they say like, oh, we applied an entropy filter. So I'm assuming that they programmatically do that. Maybe there's more data in like what's it called? In the appendix. I didn't read the appendix, or I don't even know if there is an appendix. But
Yeah,
it
I
just sounds like
imagine.
yeah.
No, go for it, Omar.
Oh yeah, no. I was just saying like, yeah, I imagine that they just apply they just say like, oh, if the entropy is greater than this in this image, then they just like discard it and do something similar, or attempt to do something similar with the other filters.
Yeah, I imagine the pipeline is completely automatic. Developing the filters is not automatic in the sense they probably need to figure out what the right threshold is, so that we
Yeah.
exclude most of the defects without losing out too much good data. But you can imagine that you have a team of 20, everyone just takes one of these filters, and then you build your evals and figure out how to cut it, get high precision and recall, and then once it's there, it's just a very simple CPU intensive task, right? That OpenCV probably has quite a few of these as well. And then once it's there, you just pass everything through. And I think that will work very well.
Yeah, but I'm
And
sure that they also did some quality control checks on a small sample subsets.
Oh yeah,
Yeah.
yeah, yeah. Yeah, I'm also sure. Yeah, okay. So let's see, data annotation. Oh yeah, so they go on to talk about their data annotation, which I think is also really interesting because they essentially have Qwen generate a JSON. So I'll actually read some of this. So we use a capable image captioner. So they're talking about Qwen 2.5 BL. They generate comprehensive image descriptions, but also structured metadata that captures essential image properties and attributes. So like instead of treating captioning and metadata extraction as independent tasks, the captioner concurrently describes visual content and generates detailed information in a structured format, such as JSON. So critical details such as like object attributes, spatial relationships, environmental context, and verbatim transcriptions of visible text are captured. So they capture key image properties and report it in a structured format. So I think that that's really interesting. I don't know how many other like labs do this, but yeah, I don't know, I just think it's really interesting that like they treated them both as the same, like image, where is it? Image captioning and like metadata extraction to like capture a bunch of different relationships from the image that might not just be captured with the image caption.
Yeah, I
So
also I thought this was really interesting in that they're actually using the vision language model in two ways. One is they're using it to annotate like this, but then they're also using it to embed the language into the vision embedding space, right? And then like sort of using cross attention to align. I thought that was really interesting that they were sort of using it in two ways.
yeah, I agree.
Thought it was pretty cool, the two papers they reference on this. Siglip 2 and Chinese clip. The Siglip 2, I looked into that paper. It's kind of interesting. It's like a very recent 2025 iteration of clip, but it's cool to see how much stuff keeps pushing there. And then they even mentioned like in that stage 3, after you do captioning, how do they still filter stuff? So like there's token length, you gotta remove stuff, you gotta filter stuff that says I can't caption this image. There's even more filters in this stuff.
Yeah. Wait, do you know what Chinese clip did differently than like regular clip?
I'm pretty sure that the captions are in Chinese.
Okay.
I haven't checked, but I would assume Chinese clip is clip in Chinese.
I meant like
The
do they
other
do anything
one,
differently in terms of like diffusion?
so they have two things that they reference. Sig clip is not Chinese clip. It's a variation that builds on top of clip, and that's not like specific to Chinese. That's from DeepMind in like February 2025. It's just an improvement on clip, but they probably merged that with the Chinese clip.
Okay, cool.
Yeah.
Right. Okay, so let's say we did that. Okay. Good data synthesis. Let's see. Oh yeah, so they talk about how apparently this is a problem with like with Chinese where like there are some characters that are just really, really rare but are still important. So I say given the long tail distribution of textual context, relying solely on naturally occurring text is insufficient to ensure adequate exposure to these rare characters during model training. So to address this, they use like a multi-stage text-aware image synthesis pipeline. It's like they have 3 stages, and they kind of describe it. So the most straightforward way to train the model to recognize and generate characters, so like they make text or they extract text paragraphs from large-scale high-quality corpora and they render it onto clean backgrounds. And so they also like implement QA or quality control. So if any character within a paragraph cannot be rendered due to limitations, the entire paragraph is discarded. So again, like they just really, really care about having like clean data. Uh yeah, so they maintain a high fidelity. Let's see. So this is an example of the first one, the paragraph that I just talked about. So they do that. So they also do compositional rendering in contextual scenes. So they just embed synthetic text into realistic visual context. So they use Qwen VL Captioner to generate descriptive captions for each synthesized image, capturing contextual relationships between the text and its surrounding visual elements. So an example of this is like this right here. And the third is, let's see, complex rendering and structured templates. So they follow complex structured prompts involving layout sensitive content. So we propose a synthesis strategy based on programmatic editing of predefined templates such as PowerPoint slides or user interface mockups. This is kind of what I was talking about at the very beginning, where they kind of use some of their PowerPoint slash like synthetic, quote unquote, synthetic images, to kind of like teach it to follow instructions or like, teach it to like how to place different, like how to use graphics or like manipulate graphics. So like again, this is an example of that.
I thought this section was very interesting, right? Because what they're doing here is they're generating a very different form of synthetic data, right? This is not synthetic data from a diffusion model or like an LLM that's just added. Like you're not really doing distillation. The first one, the pure rendering is very interesting, right? They're basically writing paragraphs, like they're extracting text and just rendering it onto clean backgrounds. Like, in Photoshop where you can like have text and just paste it into different backgrounds. That's a form of a synthetic image, but it's not a generated image, right? So they mentioned this more earlier in the paper as well, where their synthetic data gen is like very different. It's not generated images, it's text that's written and then rendered in synthetic sense. But yeah, it's like pure text. And then the thing that you mentioned with the random characters, so the part of that is actually that in languages like Chinese, there's tail end characters that don't show up a lot, right? Like you just won't see these that often, but you still need to be able to understand them. So this synthetic text properly brings back in the tail end of distribution that you don't see. So it's like, in English, we have like only so many characters, right? 26 letters, they're pretty distributed. But in Chinese, there are characters that don't show up and they render them and then they synthetically add them back. But it's a very different type of synthetic data gen.
Yeah.
I'm pretty surprised it works as well. Like, yeah, they just have templates of PowerPoints and then they just add in words,
Yeah. I'm also kind of surprised because like I thought that if there were rare characters and they would rarely show up in like in these like pure rendering, like these types of images. But I mean maybe they artificially like maybe they just like manually found which characters are rare and just like ensured that there are more of those available since
Oh,
they could
that's
have just
exactly
generated
what
more of
they
these.
did.
Yeah, I
Yeah.
can
So
imagine that's
those
what they did.
that's not a real image. That's a paragraph of text that exists, and then they just paste that onto a green
Oh
background.
yeah.
But this is not an image that exists, right? That's why it's
Oh,
synthetic.
oh yeah,
It's
yeah,
not
yeah.
telling a model to generate something with this. They actually just purely printed out this paragraph and then overlaid on a green background. And same thing with the ones below. That's what makes this unique form of synthetic data gen, right? Because it's just image editing, but it's not generated per se. And
Yeah.
then they do
Okay,
this,
cool.
they adjust font, sizing, spacing, all that stuff. And then, when you type out this paragraph, if one character is off, they discard it. So it's pure clean.
Yeah,
And this helps
okay.
with like
That's
tiny
really
text
cool.
too, I think they said. So like they can super scale it down, and as long as it's correct, have synthetic small text.
Yeah, that's really useful then. Yeah.
Yeah.
Yeah,
But
cool.
the cool thing is, after you do this, like in the second blob there of text being overlaid, sorry, if you go up a little bit,
Oh, this.
the second one, like, this I love you too. So this is text that was thrown on a piece of paper in a background. They still have to pass this back in through their captioner, right? So even though it's like fake image, not synthetically generated, they have to still throw it in the captioner and have descriptions without metadata and stuff. So it's cool.
Yeah. Does anyone else want to say anything? Okay, cool. Yeah, so this is the pre-training. So like first I'll just read some of it. So they adopt a flow matching training objective to pre-train Qwen Image. So it facilitates stable learning dynamics via ordinary differential equations while preserving equivalence to the maximum likelihood objective. So this is essentially like the diffusion part of their model. So like let's see, they have yeah, so yeah, you can throw it into ChatGPT if you want. But like essentially they train the data to point towards I think like or they start with noise and they train like the noise to point towards like the actual bona fide data. Let's see. Yeah, then the model trained to predict the target velocity, and the loss function is defined as the mean squared error between the predicted output and the ground truth velocity. So use like a mean squared error. So they try to get the velocity to match So essentially you get it to like point in the direction of the real data, like in this distribution. Yeah, so they also talk about how they optimize their models for like GPU usage. So they use something called like what they call a producer consumer framework. It decouples data preprocessing from model training. So this design enables both stages to operate asynchronously and at optimal efficiency. So on the producer side, the selected data is encoded into latent representation using MLLM models and VAE. So like they have two types of GPUs. Like they dedicate some GPUs to like do the producer's work, and they dedicate some GPUs to do the consumer's work. So the consumer GPUs are dedicated exclusively to model training, and every data parallel group asynchronously pulls preprocessed batches directly from the producer. It's like again, like they have let's see. Yeah, so they have like their pre-produced GPUs, they encode like the data to latent representations, and they just like stack them up somewhere in memory or in storage. And whenever the consumer GPUs like whenever they finish with their previous batch and they're ready, they just like asynchronously pull the data. So I think that's interesting. So let's see. So distributed training optimization. So they use like a hybrid parallelism strategy. So they combine data parallelism and tensor parallelism to efficiently scale training across large GPU clusters. So this is like less, it's like I'm less confident of like what this or like of the specifics of this part. So if anyone wants to like jump in, they're like more than welcome to. They also talk about like distributed optimizer and activation checkpointing, like to alleviate GPU memory pressure with minimal recomputation overhead during babprop. So we experimented with both distributed optimizers and activation checkpointing. However, activation checkpointing introduces substantial computational overhead in the backward pass, which can significantly degrade training speed. So they observed that enabling activation checkpointing reduced per GPU memory consumption by 11%, but like at the cost of increasing per iteration time by essentially almost 4 times. So from 2 to 7.5 seconds per iteration. And like they say that based on the trade-off, they ultimately opted to disable activation checkpointing. So I think that was pretty interesting.
Yeah, I think there's an important point here, right? In the sense that with activation checkpointing, you're like 75% slower. But you only save like 11% in GPU memory. In a sense, you could sort of reduce your batch size and actually go way faster, and it would actually make up for it. In some of my experiments, I mean, the default, if you ask Claude to write some code, the default is to enable activation checkpointing. I think because everyone's was fine-tuning on very small LLMs, and yeah, I think in Hugging Face, the default is just to enable activation checkpointing. But when you turn it off, at least I was able to see a 20% speed up with not very much increase in memory either. So I think it's something to observe. Something if you do train your own models or fine-tune your own models, like do consider not using activation checkpointing, just for your training loop to run faster. So it's nice to see another data point here in this paper.
Yeah. All right. Would a middle point in that trade-off just be to have activation checkpointing, but just to like checkpoint it less frequently? Like, wouldn't that work?
I don't think that works that way. I think activation checkpointing is needed every time you do a backward pass and optimization. So you definitely need
Oh,
to do that. Yeah.
okay. Interesting.
Yeah. So I mean, try it for what it's worth. If you have extra memory on your GPU, or you can afford to go with a smaller batch size and just do gradient accumulation, I think it's definitely, I mean, in this case, it's definitely worth the trade-off not doing the activation checkpointing. I found the same thing in my own use case as well. So yeah, something to think about.
Okay, cool. Keep that in mind then. Yeah, so we talked about this kind of earlier with, oh no, there we go. Yeah, so I kind of talked about this earlier with their data synthesis, like, or their data curation pipeline. But so onto training strategy, they adopt a multi-stage pre-training strategy aimed at progressively enhancing data quality, image resolution, and model performance. So again, they enhance their resolutions. They go from low to high resolution. So they go from 256 to 256 pixels up to 1328 by 1328. So they enhance the model. Let's see, where is it? Yeah, they let the model capture more detailed features leading to better performance. So I'm reading like right here. Richer features, specs, or spaces facilitate improved generalization to unseen data. So transitioning from low resolution to high res on flower images allows the model to discern finer details such as petal textures. So it's interesting. So they also go from non-text to text. So they progressively introduce images containing like render text. So the model can like learn visual representations and subsequently acquire text rendering capability. So they also go from massive to refined data. They gradually employ increasingly stringent data filtering mechanisms to select higher quality data. So it ensures that only the most relevant and high quality samples are leveraged to ensure training efficiency. It's cool. They also have balanced data distribution, so from unbalanced to balanced. So it mitigates the risk of the model overfitting to particular domains or resolutions, and like just lets the model generalize better. And lastly, they have synthetic data, so from real world to synthetic data. So here they just generate supplementary samples, enriching the dataset and ensuring more comprehensive coverage of diverse visual domains. They say it enhances the model's ability to generalize and perform robustly across a wider range of scenarios. So it seems pretty useful. So on to post-training and RL. So they have they have supervised fine-tuning, RL, and DPO, and GRPO too. So they use human annotations to address specific shortcomings. This is in the supervised fine-tuning phase. So they make the selected images clear, rich in detail, bright, and photorealistic, and like all that good stuff. And they guide the model towards producing content with greater realism. So with RL, they use DPO. The DPO, like it excels at the flow matching, which is the diffusion part of the image generation. And GRPO performs on-policy sampling during training and evaluates each trajectory with a reward model. So let's see. Yeah, so for DPO, it says given the same prompt, multiple images are generated with different random initialization seeds. So like with prompts without image reference images, annotators are asked to select the best and worst samples along the generated images. So I don't know if selecting the best and worst samples, I don't know if this is new or if like people have previously used this. But I thought that was interesting because like usually with DPO, I just hear people selecting the best images or like the best like whatever. Let's see. So yeah, so DPO, they use that for flow matching, and for GRPO, they use it for what's it called? They use it for like the reverse. I think they also use it for flow matching. I'm less sure of this part, but they use it for like I'm pretty sure they use it for reconstructing the image, or, like finding the loss. So if anyone wants to like comment, they can jump in here too. But if no one has anything to say, then I'll go on to the next section. Yeah, so let's see. That. Yeah, so let's see. So in addition to text image, so they let the model explore like multimodal image generation tasks. So it's not only like giving the model a prompt, which is text only, they also let the user like give it a prompt and an image. So that's cool. So they also find that providing the visual semantic embeddings from the MLM enables better instruction following. So this is kind of like what they talked about like at the very beginning, or not at the very beginning, but like what they talked about previously, where they took the last latent representation of Qwen, like of their multimodal language model. They took the last image and they kind of like fed that into the model, and they say here that it helped. So it's pretty good for them. And they also use like they talked about how pixel level VAE embeddings further enhances the model's ability to preserve visual fidelity and maintain structural consistency. So I was kind of talking about that earlier too. So yeah, so I think like I don't know, this really reminds me of like System 1 and System 2 and how like different labs have been using that. Like I remember DeepMind used System 1 and System 2 for robotics. And I think like Figure AI used that for like they also use that for robotics. So I don't really have a lot of notes on this. So human evaluation. So let's see. Yeah, these are just evaluation benchmarks. I kind of like put more emphasis on how the model was trained in like the data curation than like the human eval. Yeah, so they have like this. So there are different benchmarks. So you can read these if you want. Yeah, so let's see. Performance. Let's see. Yeah, I really just like left the benchmarks alone. And like if people want to read them, I just let like you can read them if you want. So they also let's see. Uh yeah, they also have like image editing benchmarks. Very nice. Oh, and they also have like so in some of their editing benchmarks, or in one of them rather. So they have like very dense PDFs, and they like essentially just let the model see or like they let the model like try to reconstruct some of the images to like see if it could generate some of it. And apparently it does pretty well. So like again, they focus on like English, Chinese, and like multi-object generation and spatial relationship generation. So that's kind of it. That's most of the thing that or that's most of what I focused on like in my annotation. Yeah, so does anyone have any questions or anything else or any comments?
That was pretty awesome. Thank you for taking us through this paper, Omari. I think the conclusion is also quite eye-opening in the sense that they try to they make this claim that a generative model can effectively perform classical understanding tasks, and they say that the Qwen image model is deliberately does not optimize for photorealism and or aesthetic quality, but really tries to optimize more for aligning text and image. I think you sort of tells you where they are trying to bring this model towards, right? Essentially like creating posters, creating PowerPoints. Essentially it's more practical instead of just generating images, but images with text. So I thought the conclusion was quite worth trying to read and understanding what they mean by it as well. Especially the last paragraph. So that was pretty cool. Thank you.
Yeah, okay. Yeah, I'll just like read it. But well, like other people can ask questions.
Anyone have any questions?
So
Okay, I guess so. Go for it.
Yeah. So they mentioned that the model's training data pipeline does include other languages, but I see that most of the benchmarks were focusing on English and Chinese. So I don't know if in the conclusion, do they specify that they can handle other languages?
Yeah, so actually I'm not sure. They don't really talk about like other languages besides English and Chinese.
Yeah.
So I'm not really sure. I kind of
They
like I
had-
tested Qwen.
They had a category for other. They
Yeah.
had English, Chinese, and other, but I don't think this thing will do other languages.
Okay. Maybe others to exclude them or to further them?
No, they weren't filtered out. They were filtered in.
Okay.
But
Okay.
yeah, it's primarily English and Chinese.
Yeah, on page 26, it seems like they only focus on English and Chinese text rendering. So I don't know if they did evals on the other text. Maybe they just not equipped to do evals on other languages. Yeah.
They had 4 categories. They had English, Chinese, other language, and no text. So they definitely had a other language, but I don't think it's significant, you know?
Mm.
And then some of this is also like, there's already a vision encoder in there that can do multilingual, but I don't think it can specialize an output for this.
I mean, actually, I tested some of the prompts with this. I didn't test any like non-English or Chinese languages. But yeah, I mean like I tested them in Sora, like Qwen and Sora. And like actually I think the quality was like pretty similar. Or Qwen's text generation was like it was a little more clear. Like the characters were a lot clearer. You could kind of see them. It was a lot easier to look at them and just like see the background or like distinguish between the characters and the background. But yeah.
Live coding,
Um,
I'm testing it in Spanish.
Yeah, I should have.
Should we do a different language? Like, should we do Korean? Let's see.
Yeah, maybe something that's not Latin.
Yeah.
Arabic. I don't know. I don't know if we would even be able to evaluate it.
I can try
I
that.
mean, I have. Let's see. I just shut off a generation. We'll see what it outputs. Oh shit, it's not correct, but it has Korean looking stuff.
Wait, what's your prompt?
Literally in Korean. I just sent it. I went to Google Translate and I translated a sentence. Yeah, you wanna share the images I shared in Zoom chat?
Yeah.
Maybe just change it. Well, I mean, it's off, but it does look a little more Korean.
Wow, why do you say it's not correct?
Because look at what it's supposed to write.
The first character, right?
Actually,
Maybe it fixed it. I actually don't know. Wow, this is really,
oh, I guess the second line is kind of there.
yeah. Maybe the first line actually, I actually don't know. Maybe it's a
Kind
haha.
of there, kind of
And
there.
they actually fixed it. Oh, it's
Okay,
actually
maybe,
coffee. Oh, okay.
but okay, it does something.
Wow, this is actually pretty good.
Yeah, I don't know if that's right or not. I don't speak Korean.
It looks similar, actually. Oh my God, it does Korean. We're cooked. Okay, I did another one. I'm now trying to translate the text it generated. I showed another image if you want to swap to it.
Yeah.
This is
And then I'm
actually
translating
pretty
this
good.
with Korean model. And see if it's coherent or if it's just random stuff. Yep.
Yeah,
So
it's
it
that one.
put Korean on the board. I'm trying to have it. Oh my God. Translate this Korean. It's struggling. Okay, I think this is enough live coding.
Oh yeah, someone said the fuzzy background characters don't look Korean.
I mean, it could also just be style, right? Like it is also a monkey.
That's true.
I guess.
So the second image is nonsense gibberish according to translations. I
But
guess I
like the
did
main,
ask
yeah,
it for random text.
yeah, but the font of the main text and the background text do look different. But oh well.
Yeah, it's cooked.
Oh well, they tried.
I'm doing another.
All right,
Oh my
cool.
God.
I think next week we have, was it Venki again? Yeah, Venki will talk us through GLM. Wow, this chalk text actually looks so much like chalk. I'm actually impressed, but I don't deal with a lot of image
All
gen.
chalk.
So
I thought the chalk looks mid.
no, the one that Steve just posted, at least the first character.
Oh, yeah, it's pretty good. It's pretty good. I mean, it's
Wow,
trained specifically on this type of
I'm
stuff.
impressed for the first character at least. Yeah.
Frankie,
Yeah, I
you
like the
have
chalk
hand
scratches.
raised. Do you wanna-
Yeah, so sorry, maybe a late question here. I was going over that the flow and diffusion model that they had in 4.1, and I just want to make sure that I understand because so I think that they have a joint latent space of image and text, correct? And
Yes.
so they're applying a noise model on top of that space, right? So, and I was wondering, like, typically when you add noise to, say, latent space of text, it doesn't work very well. That's why we don't have very good diffusion models for text. So, I'm kind of surprised that this kind of like works. So I'm not sure what you guys feel about that. Because so what I'm saying is that their latent space is kind of like a multimodal one, right? It contains both image and text related stuff together. And typically diffusion, as you have here, which is adding noise to that, normally doesn't work well on text-based latent space. So I was wondering like why this would do any better.
So one
Yeah.
thing that I noticed was that if you look at the architectural diagram, the noise is only added on the image side.
Oh,
So
okay.
I think can you, if you scroll up to the architectural diagram, I might be wrong about that. It's just from memory, but I think that's what I saw. Yeah, so the noise is only added on the image side. And then you have this cross entropy thing that combines them. So it looks like it's more like conditioning on the text using building the common latent space inside of the transformer blocks.
Okay, so it's like normal diffusion then, right? Like normal image diffusion.
Yeah, seems like.
Yeah.
Okay.
I also think it's because like the resulting product of the model will be an image, like which is continuous, like in diffusion space. Like if the resulting product of the model would be like text or something, or like something that's like inherently discrete, then I feel like it'd be a lot different. Like you might have to use a decoder or something. But like yeah, like
Okay.
with the prompt and the image, both those get like injected into latent space, and then you can like perform diffusion on that, and like the resulting process will be an image.
Well, I think RJ said that it doesn't get injected, right? On the combined embedding. It's just on the image embedding. It gets added like on this figure. The noise only added to the image image latent space, not to the prompt. They get combined later, but the noise is only added to the image side.
Oh yeah. Oh yeah, yeah. You're right. You're right.
Yeah. Okay, cool. Sorry. Thanks, RJ.
Yeah, cool. So it's 402 right now. So is that it?
Yeah, awesome. Thanks for guiding us through it. Next week we have another volunteer. We'll share the Luma and stuff. But cool. Thanks so much for
Yeah,
watching.
I tested it in Arabic as you requested. So yeah, of course it's not right, but there is like the same number of letters and going from right to left, but it's missing a lot. So completely rubbish.
Awesome. Well, I guess it's English and Chinese then. Cool, guys. Take care. See you guys next week.
Okay, bye.
Bye.
Okay, cool. Bye.